Welcome to Ring Theory. Today we are going to unlock one of the most elegant and powerful tools in algebra, known as Eisenstein's criterion. Imagine trying to break open a heavily locked safe without the combination. Factoring large polynomials can feel exactly like that, frustrating and nearly impossible. But what if you had a magical security scanner that could instantly tell you if the safe is a single unbreakable block? That is exactly what this criterion does for polynomials. Let us dive in and see how it works. Before we look at the criterion itself, let us understand why we need it. In algebra, we constantly ask if a long polynomial can be broken down or factored into smaller pieces. If it can be factored into smaller polynomials, we call it reducible. If it is built as one solid, unbreakable mathematical piece, it is irreducible. Factoring by guessing is incredibly time-consuming. Eisenstein's criterion gives us a brilliant shortcut. It is a specific test using a prime number. If a polynomial passes this test, we can guarantee with absolute certainty that it cannot be factored over the rational numbers. Now that we know what irreducibility means, let us look at the mathematical setup. We start with a standard polynomial, which we call f of x. This polynomial must have integer coefficients, meaning the numbers in front of the variables are whole numbers. The symbol n represents the degree, which is the highest power of x. The term a sub n is our leading coefficient, sitting at the very front. At the very end, we have a sub 0, which is the constant term, because it has no x attached to it. As the degree n gets larger, factoring becomes a nightmare, which is why we need a prime number test. This brings us to the first of three strict conditions in Eisenstein's criterion. To use this test, we must pick a single prime number, which we call p. Remember, a prime is a number like 2, 3, 5, or 7. The first rule states that our chosen prime p must absolutely not divide the leading coefficient, a sub n. The vertical line with the slash means does not divide. If your prime does divide the front number, the test fails immediately for this specific prime, and you must either try a different prime number or use a completely different mathematical strategy. Moving on to the second condition, we look at the rest of the polynomial. This formula tells us that our prime p must perfectly divide every single coefficient, from the constant term at the end all the way up to the term just before the leading coefficient. The vertical line here means divides evenly. This is the core of the scanner. You must check every single middle and end term. If even one of these coefficients is not divisible by your prime p, the entire test fails for this prime. It is a strict checklist, and every box must be ticked. Finally, we reach the third condition, which acts as a crucial safety check. We take our prime number p and square it. This squared value must not divide the constant term, a sub 0. Why is this important? If p squared does divide the constant term, the polynomial might actually be reducible, and the criterion cannot guarantee anything. Only when all three of these conditions hold true simultaneously, p does not divide the front, p divides everything else, and p squared does not divide the end, can we confidently declare that the polynomial is irreducible. Let us visualize these three rules together to see how simple the checklist really is. Look at the diagram on screen. You scan the polynomial from left to right. First, look at the leading coefficient on the far left. Your prime p must not divide it, indicated by the red cross. Next, look at all the remaining terms to the right. Your prime p must divide every single one of them, shown by the green check marks. Finally, look at the constant term at the very bottom right. The square of your prime must not divide it. If your polynomial matches this exact visual pattern, it is unbreakable. Before we prove why this works, let us see this criterion in action with a concrete example. We are given the polynomial x cubed plus 2x plus 2, and we need to find out if it is irreducible. First, we list out all the coefficients. The highest power is 3, so the leading coefficient a sub 3 is the invisible 1 in front of x cubed. There is no x squared term, so a sub 2 is exactly 0. The coefficient a sub 1 is 2 and the constant term a sub 0 is 2. Since the number 2 appears frequently, we will choose the prime number p equals 2. Checking the first condition. 2 does not divide the leading coefficient 1, so the first condition passes perfectly. Now that the first condition is met, let us check the remaining 2. For the second condition, our prime 2 must divide all the middle and end coefficients. 2 divides 0 because any non-zero number divides 0. 2 also divides 2 and it divides the constant term 2. So the second condition is satisfied. Finally, for the third condition, we square our prime 2 to get 4. We check if 4 divides the constant term 2. Since 4 is larger than 2, it obviously cannot divide it evenly. The third condition is satisfied. Because all three conditions hold true for the prime 2, Eisenstein's criterion guarantees that this polynomial is irreducible. It cannot be factored any further. So we have successfully used the criterion. But why does this magical checklist actually work? Let us prove it using a method called proof by contradiction. We will assume the exact opposite of what we want to prove. We assume our polynomial f of x is actually reducible. This means it can be factored into two smaller polynomials, which we will call g of x and h of x. We write out g of x with coefficients b and a degree r. We write out h of x with coefficients c and a degree s. Because they are smaller pieces, both r and s must be greater than 0, and their sum must equal the original degree n. We will now show that this assumption breaks the fundamental rules of mathematics. Let us continue by looking at the constant term. If we multiply g of x and h of x together, the only way to get the constant term a sub 0 is by multiplying the two smaller constant terms, b sub 0 and c sub 0. Now recall our third Eisenstein rule. The prime p divides a sub 0, but p squared does not. Because p divides the product, it must divide at least one of the factors. But it cannot divide both. If p divided both b sub 0 and c sub 0, then p times p, which is p squared, would divide their product. This violates our rule. Therefore, p must divide exactly one of them. For our proof, let us assume p divides b sub 0 but does not divide c sub 0. Next, we examine the leading coefficient. The only way to get the leading coefficient a sub n is by multiplying the leading coefficients of the smaller polynomials, b sub r and c sub s. Remember our first Eisenstein rule? The prime p does not divide a sub n. Because p does not divide their product, it cannot divide b sub r and it cannot divide c sub s. So, look at what we know about the coefficients of g of x. The prime p divides the first coefficient b sub 0, but it does not divide the last coefficient b sub r. This means that as we move up the list of coefficients, there must be a specific point, an index k, where p suddenly stops dividing them. This brings us to the final step of our proof. Let us write out the formula for the kth coefficient of the original polynomial, a sub k. Because k is strictly less than n, our second Eisenstein rule says p must divide a sub k. Now look at the right side. We defined k as the first index where p does not divide b. This means p divides all the previous b terms from b sub k minus 1 down to b sub 0. For the equation to balance, p must also divide the very first piece, b sub k times c sub 0. But wait, we already established that p does not divide b sub k and p does not divide c sub 0. A prime cannot divide a product if it divides neither factor. This is a mathematical contradiction. Our assumption was wrong, giving us the final result. The polynomial must be irreducible. Now that we understand the proof, let us look at a more advanced scenario. Sometimes a polynomial does not pass Eisenstein's criterion immediately, but we can slightly alter it to make it work. A famous example is the pth cyclotomic polynomial. If you look at its formula, every single coefficient is exactly 1. Because no prime number can divide 1, Eisenstein's criterion fails immediately on the first glance. However, we do not give up. Our strategy is to shift the polynomial by substituting x plus 1 in place of x. If we can prove that the shifted polynomial is irreducible, then the original polynomial must also be irreducible. Before we perform the shift, we use a clever algebraic trick. The long string of terms in the cyclotomic polynomial is actually the result of dividing x to the power of p minus 1 by x minus 1. This is a standard formula for the sum of a geometric series. Writing the polynomial as a compact fraction makes the substitution much easier to calculate. Instead of plugging x plus 1 into a dozen different terms, we only have to plug it into this single elegant fraction. Let us see how this substitution transforms our equation. Let us apply this shift step by step. Everywhere we see an x in our fraction, we replace it with x plus 1. In the numerator, we get x plus 1 all raised to the power of p minus 1. In the denominator, we get x plus 1 minus 1. The denominator simplifies beautifully. The plus 1 and minus 1 cancel each other out completely, leaving us with just x. Now we have a much simpler expression, but we still need to expand the numerator to see the individual coefficients and apply our prime number test. To expand the numerator, we use the binomial theorem. This gives us a series of terms featuring binomial coefficients which represent combinations. Notice that the very last term of this expansion is a plus 1. When we subtract the minus 1 that was already in our numerator formula, they cancel out. Now, every remaining term in the numerator has at least one x in it. We then divide the entire numerator by the x in the denominator. This reduces the power of every single term by exactly 1. We are finally left with our new shifted polynomial ready for Eisenstein's test. Now we apply Eisenstein's criterion to this new polynomial using the prime p. We check the first condition. The leading coefficient is 1 and p does not divide 1, so it passes. Next, the middle coefficients are all binomial coefficients. A known property of prime numbers is that a prime p always perfectly divides the binomial coefficient p choose k, as long as k is between 1 and p minus 1. So, the second condition passes. Finally, the constant term is exactly p. Since p squared does not divide p, the third condition passes. All conditions are met. This gives us our final answer. The shifted polynomial is irreducible, which proves the original cyclotomic polynomial is also irreducible. You might be wondering, why does Eisenstein's criterion matter in the real world? While factoring polynomials might seem like an abstract puzzle, it is actually the foundation of modern cryptography and computer security. When you send a secure message online, the encryption often relies on mathematical structures called fields. These fields are built using irreducible polynomials. If a hacker could easily factor these polynomials, they could break the encryption and steal your data. Eisenstein's criterion gives mathematicians and computer scientists a fast, reliable way to prove that the building blocks they are using for these security systems are genuinely unbreakable. Let us summarize the key takeaways from today's lecture. Eisenstein's criterion transforms a difficult algebraic factoring problem into a simple checklist of divisibility. Remember the 3 rules. Your chosen prime must not divide the leading coefficient. It must perfectly divide all the middle terms and the constant term. And its square must not divide the constant term. If all 3 hold, the polynomial is guaranteed to be irreducible. And as we saw with the cyclotomic polynomial, even if the test fails at first, a clever algebraic shift can reveal its hidden unbreakable nature. You now have one of the most elegant tools in ring theory at your disposal.